Welcome, welcome, my students. How are you there? I'm also fine. Today, we are going to look at our mathematics paper 2. That is the mechanics part. We are going to look at the part of mechanics. We had started with our first unit, and that was linear motion. Linear motion, the one we call motion in straight line. Is that okay? So we looked at our first topic in mechanics as motion in a straight line. Is that okay? So, and we looked at a number of elements under that. We looked at what linear motion is, the forms of how body can move in a straight line. We looked at the body projected vertically upward, the body moving horizontally. All those ones, we described them as linear motion. And then we tried looking at some simple elements that will make us analyze this topic here very well. And that was the element of speed and velocity. We looked at what would be the difference between speed and velocity, such that if it comes to ideas of calculation, we don't contradict the two. Is that okay? So we looked at that one, and then we also looked at distance versus what we are calling displacement. Is that okay? So we analyzed all those ideas. We looked at the difference and how can we best use them. If they ask you, find the displacement, find the distance. What are they exactly meaning in such a kind of idea? If they say find the average speed and find the average velocity, what are they exactly meaning? That is what we analyzed and looked at some few examples. So, having done that, we can also look at one more example as we go to a new thing. We can look at one example, and that is the points A, B, and C lies in a straight line. Lies in a straight line with AB equaling to 60 meters and the AC equaling to 80 meters. And then a particle, or I can call it a body, travels from A to B, from A to B at an average speed of 10 meters per second, and then from B to C in time of 4 seconds, and finally traveled back to point B. And then you can say if the average speed for the whole journey is 5 meters per second, and then you're supposed to part A find the average speed for the second part of motion, that is to say from B to C, and then part B I would say find the average speed for motion from A to C. And then part C, I can ask you to find the time taken to move from B, from C to B. And then lastly, I would ask that find the average velocity for the whole journey. Is that okay? So we have here our simple example that we should look at, and then we see how we can apply the idea we have just looked at. That we have 3 points. We have 3 points. They are A, B, C. They lie in straight line. Is that okay? So in our simple sketch, okay, in my simple sketch, I would look at this being a straight line. Is that okay? I would look at this as being a straight line that they're talking about. And then I can note this point as point A. And then I note this point as point B. And then I note this one as point C. Is that okay? So these are the 3 points we are talking about. That this point A, B, C, they are all in straight line. And they have given us that these points, A and B, the distance from A up to B is given by 60 meters. Is that okay? And then they're also saying that AC is equal to 80 meters. That means that if I could simplify that, I would say this is 20 meters, because they have said from point A to point C is 80 meters. Is that okay? And then also they are saying that there is a body which started moving from point A, it went to point B on an average speed. The speed on average moving from point A to point B, the speed was, I would call it U, as 10 meters per second. Is that okay? And then they said this body here traveled to point C. It didn't just end at point B. It continued to point C, and they have given you the time taken to move from point B to C as equivalent to 4 seconds. Is that okay? From point AB is 60, AC is 80, and that means BC is the 20. So that this plus that gives the total of the 80. And they said the body traveled from A to B with the average speed of 10. And then what happened next? It traveled from B, went to point C, and that is in a time of 4 seconds. Is that okay? And then they said, and finally traveled back to point B. This body here, after reaching point C, it decided now to move back to point B. Is that okay? It traveled back to point B. And now they are saying that what is interesting is that if the average speed for the whole journey is 5 meters per second, average speed for all journey has been given to you. Average speed for whole journey is equivalent to 5 meters per second. Is that okay? Now, they are telling you to find the average speed for the second part of motion. And in other words, the second part of motion that is moving from B to C. Is that okay? They want you to find the average speed of moving from B to C. How do you get the average speed in that case. Have the duster here. So, if we are to find the average speed, from what we looked at, how do we calculate the average speed? We said our average speed is equivalent to the distance over the time taken. Do we still all remember that? That average speed can be calculated from distance over the time taken. Therefore, if I'm looking at the average speed of moving from B to C, I should be in position of identifying the distance B to C. Is that okay? And also the time in B to C. If I identify the distance B to C and then the time from B to C, I will be in position of calculating the average speed in that scenario. Is that okay? And that means that I'll say my distance B to C, the distance B to C we say is equivalent to 20 meters. That means that I'm going to say here I have 20 meters divided by the time also. The time should be BC. Is that okay? The time should be BC. And we were given from our question that the time B to C is equivalent to 4 seconds. And now that will give us something like 20 divided by 4, and that is our 5 meters per second. And now you can make a conclusion that therefore the average speed of moving from B to C is 5 meters per second. Is that okay? That is the conclusion we are getting from there. We say to calculate the average speed of moving from B to C, we should use the formula that average speed is distance over time. And we said that by the fact that we are looking at distance B to C, by the fact that we are looking at average of B to C, that means our distance here, okay, the distance we are using here should be distance BC. Even the time here should be distance from, should be time of B to C. And we say distance B to C, from our illustration here, we realize that it is 20 meters. And then again, we are saying that the time was given as also 4 seconds. So we can say it is 20 divided by 4 to get 5. If you divide using your calculator, you'll realize that the answer we are getting here is 5 meters per second. Is that okay? That is for the first part. This is for the first part. And I would go to part B. Part B is saying that find the average speed for the motion from A to. Now we have changed our concept from looking at B to C, but now we want to look at from A up to C. We should also find the average speed. Interestingly, we are also going to say if we are to analyze motion from A to C, and again we still need the average speed, the same formula still works. Only that what is going to be right here is that the distance we should be looking at should be distance AC. And also what should be very true, the time we should be looking at should be the time of traveling from A to C. Is that okay? So if we have those two, we shall just now use our formula that distance, average speed equaling to distance over time. Is that okay? And it is very nice that we can now say that average speed still, if I can repeat, is equaling to distance AC over total time in AC. Is that okay? That is what we should exactly look at. If you want average speed of AC, it is very true that we should look at the distance AC and then also the total time in AC. Is that okay? But now ask yourself, are we having distance AC? True, we are having distance AC as the 80 meters. And then ask yourself, are we having the time taken to travel from A up to C? If you check here properly, you realize that we have the time B, C, but we don't have the time A, B. Is that okay? So that means that we should first get the time taken to travel from this point to this point. Is that okay? We should know the time from this point to this point here. So I should look at but time for AB should be equaling to distance AB over speed, average speed in AB. To first know the time in AB, and then I add it to the other one to know the total time of AC. Is that okay? So distance AB. What is our distance AB? Our distance AB is equal to 60 meters. Divide by our speed or average speed in AB. This is letter B. Speed, average speed in that, and that is equivalent to 10 meters per hour. You realize that this is giving you 60 seconds. Is that okay? So it is now becoming true that the time taken to move from point A to B is equivalent to 6 seconds. Is that okay? So now I know the time here is equivalent to 6 seconds by calculation. And I know the time taken to travel from this point to this point is 4. That means I can know the total time of A to C as that plus that. Is that okay? This is my second. So, now, after doing that, we are now going to substitute in our formula. We are going to substitute in our formula, and now we shall say average speed is equivalent to distance AC. Our average speed in AC will be equivalent to the distance AC, which is 80 meters divided by the total time in AC. We say now to get the total time AC, we shall say time here plus this time, so that we get AC. Time in AB plus time in BC gives us time in AC. That is 6 plus 4, which is 80 meters out of 10 seconds. Is that okay? And that is giving you an element of 8 meters per second. Is that okay? 8 meters per second as our average speed of moving from A to C. Is that okay? So we say that if you are to find the average speed of motion from A to C, our general formula is average speed is given by distance, okay, divided by time. That is the general formula we are going to use. And we said that in a scenario where we are looking at average speed of A to C, that implies that the distance we are looking at should be also distance A to C. The same thing that the time taken, the total time taken, should also be AC. If you have distance AC and also time AC, you will use now our formula to get the average speed of A to C. Is that okay? And then we asked ourselves, are we having the distance AC? We went on our diagram following what the question was telling us. The diagram was telling us that the distance AC was given as 80, and then we realized that we have distance AC. And then we said, what about the time in AC? To fall back to our question, we realized that we only have time of BC, but we need AC. That means that we should be having, first of all, the distance, the time AB, and then if we get it, we are now going to add it. We are going to add it to the one of BC to get a total time of AC. Is that okay? And then we said that now, to get the time of AB that we're interested in, that we want to get and add on this, we said that we are now going to use the same idea that time for AB will be distance AB divided by average speed in AB. Everything is AB. Is that okay? And the distance AB was 60 meters. And then the average speed in AB was the 10 meters per second. Then if we divide that, we are coming up with 6 seconds. That means that it took 6 seconds to travel from A to B. And now if we add the distance, that means the time to travel from B to C, we would have gotten the total time of A to C. And that is equivalent to 10 meters per second. If you add 4, I mean 6 plus 4. And then we said we can now fall back to our statement and say that the average speed of AC is equivalent to 80 divided by the sum of the total time. Is that okay? Or divided by the total time. And then we say that will be 80 plus 10. 80 divided by 10. And then if it is 80 divided by 10, that is definitely what we are saying is the 80, that is 80 meters per second as the average speed that you can conclude and say, therefore, the average speed for distance AC is 8 meters per second. Is that clear? If that is clear now, we can now look at another part. We can now try to attempt another part. The next part, that is part C, they are asking us to find the time taken to move from C to B. That what do you think could be the time now in moving, because they described the motion as the body moved from point A to point B. And then it moved from point B to point C. And then it moved from point C back to point B. Is that okay? So now they are asking us, what do you think could be the time taken to move from point C to B? Is that okay? It is very unfortunate that you will find someone thinking that if a body moves from point B to C in 4 seconds, and then also tempted to think that it can move back in the same time, it is definitely very wrong. Is that okay? It is definitely very wrong, because it is not true that the speed it used in moving here is the same speed it would use in moving back. If that was very true, that the speed it used in moving from here up to here, it used the same speed, in that case, we would be in the position of saying that the time taken to move back would be the 4 seconds. But we are not definite about it, that it moved using the same speed while moving it behind. Therefore, we should calculate that time. And I can now say, let T be the time taken to move from point C to B. Is that okay? From average speed for all journey will be equaling to total distance for all journey. Okay, you divide by total time for the whole journey. Remember in the question, we were given average speed for the whole journey. Is that okay? They have given us the average speed for the whole journey. So that means that where we have the average speed equaling to distance over time, if the average speed now is aiming at the one of the whole journey, that means the distance should be for the whole journey and also the time should be for the whole journey. Is that okay? And it will now become very true that the total distance for the whole journey will be equaling to distance AB plus BC plus CB divided by the time in AB plus time in BC plus time in CB. Is that okay? That if we are to look at the average speed for the whole journey, which would be total distance for the whole journey divided by the total time for the whole journey, we would now say that the whole journey was involving moving from A to B, and then from B to C, and then from C back to B. That is, if you add all those one, you'd be in position of getting the total distance for the whole journey. Is that okay? And then if we are to look at the total time for the whole journey, it would also be equivalent to the time taken to move from A to B, that is TAB, and the time taken to move from B to C, that is TBC, and then to move back from C to B, that is this. Is that okay? So now, we substitute in our formula. Let me hope you have this question there with you, so that I can wrap it off and have some space. So, if that is that, I will now say the average speed for the whole journey was given as 5. I can now say the 5, which is the average speed for the whole journey, should be equivalent to distance AB is 60 plus BC is 20 plus CB is 20. Divide by the time in AB. From A to B, we said the time is 6 plus the time in BC. From B to C, the time was 4, and then plus, is that okay? The time from C to B, and that is what exactly they're interested in. And we have called it here that let T be the time taken to move from C to B. I can now call it T. Clear? And then this one can now end in 5 is equaling to, if you add that, you'll get it as 100. Is that okay? Out of 10 plus T. Clear? And then if I'm having that, I can reduce or I can cross multiply. If at all it doesn't confuse, I can now say 5 into 10 plus T is equaling to, okay, 100. And now you can open bracket and say it is 50 plus 5 equaling to 100. I think that is 5T. Is that okay? This is 5 times 10, 50. 5 times D, 5T. Is that okay? Equaling to 100. And now you can say 5T is equaling to, you say 100 minus 50, okay? And that is 50. 5T is equaling to 50. Divide by 5, divide by 5. You will realize that your T equaling to 10 seconds. Is that okay? So the time taken to move from C back to B is equivalent to 10 seconds. Is that okay? How did we come up about that? We said that they are interested in knowing the time taken to move from point C back to B. And we said, don't even think that the time is equivalent to 4 seconds, you see. Because I know someone may say, I think if it is taking 4 seconds to move from B to C, it should also be very true that if I'm coming back, it will also take the same. We say that is only true if it uses the same velocity. The velocity it used in moving towards point C is the same velocity it is going to use in coming back. But we say we are not definite and it has not been illustrated to us. Therefore, we say we shall go into letting the time for moving from point C to B to be a letter T. Is that okay? And now we say that they have given us some good element in the question that average speed for the whole journey was 5. And then that means that we can use this to come up with that. And say that from this point that average speed is equaling to distance over time. It means that if I'm looking at average speed for the whole journey, it is also true that the distance should be the distance for the whole journey. And then the time should also be the time for the whole journey. The same thing we are doing to this other one, that average speed of AC should be distance in AC divided by the time in AC. Is that okay? So for whole journey should be distance of whole journey divided by time for whole journey. And then we say what is the total distance for the whole journey. The whole journey involved moving from A to B. That means we look at distance AB, and then continuation from B to C. That means we look at BC, and then plus going back at that point, that is CB. Is that okay? And then the time also will be the respective time in those areas. That the time should be also time in AB plus time in BC. Then finally time of C back to B. Is that okay? And I will say that if that is true, we can now say the average time which is given, that is 5, should be equaling to what is AB from A to B is 60. And then what is BC from B to C is 20. And then what is CB? CB is also 20. And then divide by the time. The time will be AB 6, BC 4. And then the other time we called it letter T. And then we placed it there as a T. And then we say the next is now just to simplify and say now 5 is equaling to this plus that plus that. We said that is equivalent to 100. Is that okay? If you have added very well, you're going to get 100. And then divide by 6 plus 4, that is 10 plus T. Is that okay? From here we cross multiply. We said this will be equaling to 10 times 1. Is that okay? That is, 100 times 1. That is 100. And then we say we shall also have 5 into this. Okay? And if you open, you'll get 50 plus this time that 5t equaling to 100. Is that okay? And now if you take this the other side, you shall have 5t equaling to 100 minus 50, which is 50. And then divide both sides, you're going to come up with the t equaling to 10. And then you say, therefore, you should always make conclusion. Therefore, the time taken to move from B to C, to move from C to B, is 10 seconds. Let me hope we are still together. That the time taken to move from point C to B is equivalent to our 10 seconds. So now let's look at the last shift of our question, which is asking to find the average velocity for the whole journey. Is that okay? We have been talking about average speed, but now let's look at average velocity. How do we get the average velocity? Let me wrap this part here. If you can still remember from our first lesson, we said that average velocity, if we are looking at average velocity, instead we should be looking at displacement with respect to time. And it should be in position of knowing what a displacement is, because we looked at the difference between what we are calling distance and the displacement. If I talk of a distance, if I talk of a displacement, is that okay? So we are going to say average velocity is equaling to displacement over the total time taken. Clear? Our average velocity is instead, if you can remember, given by displacement over the total time taken. Now, what is the displacement of this body in a scenario where it has moved from A to B and then to C and then back to B? Okay? What could be the displacement in that scenario? Remember we said if a body moved from one point to the other and then to the other and then to this, displacement will look at what is the length of the path between where you were and then where you are finally. Okay? That is what we talked about. That if I'm looking at this body moving from here then here, is that okay? Displacement is what is this distance, what is this length here? That you started here, you moved over where we don't mind, but if you're here, how far have you moved from the original, from here up to here? So, that brings us back here that if this body moves from here, comes here, and then finally here, our displacement is, okay? Our displacement is how far is it from where he started from and where he finally is what we are calling displacement. Whereas distance would be this plus this and that would be distance. But displacement, we look at how far are we from the original or starting point. So I would say now that is, displacement is this one here. That would be now 80 from here up to here, subtract away that, minus 20. Is that okay? To get the total time will be the 6 from here up to here, plus, okay, plus the 4, and then plus the time we look at the total time. You may be there thinking that we should also look at if displacement is this, we should also only use 6. However much the displacement was, the resultant displacement is 60, but that resultant displacement was performed in a total time of us going, coming. So the time we should look at the whole of it. Because getting 60 was by first moving here, and then back. Is that okay? So that means that to come up with this, we used this and that. So the time should be the whole time, but not just this. You may be thinking, if we are looking at displacement being AB, even time should be this. The time to come up with 60, we first went to the other side and then came back. Therefore, the time remains the total time. Clear? The time remains the total time. And now that will give us 60 out of 20. If you add that plus that, you'll come up with 20. And this goes away, it will result into 3 meters per second. Is that okay? So the average velocity is 3 meters per second. And as a reminder, we said that velocity is a vector quantity. Therefore, if you are describing anything concerning velocity, be in position of measuring the magnitude as well as measuring the direction. Is that okay? The moment you only aim at measuring the magnitude and then you don't talk about the direction, you are specifically meaning or you are indirectly meaning speed, if you can still recall. Therefore, to now talk about this, we can now conclude and say therefore, the average velocity is 0 meters per second to the right of point A. That is according to my diagram. That on the diagram we had drawn, point A was here and then point B was here. So this body was here, and to me this is the right of point A. So as we said, always velocity, when we're talking about it, think about the magnitude, think about the direction. To the right, to the left, due east, due south, due north, something of the kind. Is that okay? Or certain degrees, this and this. So you should always mention something like that. As a review of that, we say to get the average velocity, the formula changes to displacement over time. Whereas average speed is distance over time. And hoping that you well know the difference between the distance between distance and displacement. Is that okay? So if I'm talking about displacement being used in average speed, I'm talking about distance being used in average speed, and I'm talking about displacement being used in average velocity. You should be in position of knowing what they are. Is that okay? So we said that for this case here, we said average velocity will be displacement over time, and then the displacement will look at it. If the body moves from A to B and then back to C, displacement is that pass between, or the distance between initial position and the final position. Is that okay? Irrespective of where you passed, but where are you? How far are you from where you started from? Is what you're calling it displacement. And we said the time, we shall look at the total time. Because we said that to come up that I'm 2 meters from where you are finally. How long did you take to reach that point? Therefore, we look at the whole time of the pass, because it will take you time to move there. Is that okay? So we say that we should not look at just the time of this. We should look at the total time, because it took this pass, so the total time to move, come back. So we should use the total time. And that was now giving us 80 minus 20 to get how far is it from the other point. And then the total time was the time this plus this time, and then plus that time. That is giving us 20. And then we said that finally brings us to 60 out of 20. And that is resulting into 3 meters per second. And we said that after getting 3 meters per second, don't forget, we are looking at average velocity. Velocity is a vector quantity. Therefore, whenever you're talking about velocity, be in position of measuring the magnitude as well as the direction. And say, if this is our magnitude, and then look, where are you? This is our main point, origin, where we started everything from. This point B, where the particle finally is on the left. Is that okay? It is on the left of point A. Therefore, on the right. It is on the right of point A. Therefore, you should say now the average velocity is 3 meters per second to the right of point A. So it is to the right. Because from this is right, left. Is that okay? So that finally becomes the solution to our example. Let me hope everything has been good. After looking at all these examples here, let's try looking at some other element. And that is none other than the graphs. Let's look at the graph. In the graph here, let's look at the first part. Okay? The part A, I'll look at displacement. Displacement time what? Displacement time graphs. Clear? So we are going to look at our displacement time graph. Is that okay? We are going to look at the displacement time graph. So let's begin with the for stationary body. If I have this is displacement, which will be in meters against time, that will be in second. Supposing I have this is for a stationary body, isn't it? With zero gradient. Is that okay? We have that graph there with zero gradient. A graph for a body which is at rest. Displacement time graph. Zero gradient. Horizontal lines have zero gradient. This is for a body which is at rest. Because you're well aware that we shall look at that velocity is the change in displacement over change in time, isn't it? Change in time. So mathematically, in our derivative of math 1, we can say velocity change, you can say it is ds, isn't it? Over dt. Is that okay? Velocity can be ds dt. Velocity is the rate of change over displacement. Is the other one change in displacement over change in it? So we can write for smaller changes, you can just write it ds dt, meaning change in displacement over change in time. That is it, velocity. That is ds dt. And now we are saying that what is very true, if you look at this velocity here, if you look at this graph here, at every point, because here we are supposed to get displacement, the displacement is a constant, but the time is changing. There is this change here is zero. Don't you think 0 over dt is 0? That means that v equaling to 0. And if there is no velocity, what do you think is that? That is a body which is at rest. And that's why I've decided to say this is a stationary body. Because if there is no change in the distance, but the time is going, that means that someone was just standing. He's not changing his position, but time is going. Is that okay? So that is for a stationary body. Displacement against time for body which is at rest is drawn like this. Is that okay? I've explained it using this fact that velocity is changing the distance over changing time or rate of change over displacement. If we talk about rate, we are looking at time. So in simple understanding, we say it can be written as ds dt for smaller changes, but we are still meaning the same thing. And we say that if you look at this graph here, this being a constant, it means that as time is going, if here we had maybe some distance from the origin, it is 20 everywhere. So that means that body remained at 20 for some long time. So if a body is at one point for a long time, we can now say that body is stationary. Is that okay? So we shall say that if the s is not changing, is 0, divided by time, that means v is 0, and therefore it will imply that the body is stationary. And then let's look at for another body. If I look at this one here, this is as well still displacement in meters, and I have here time in second. What do you think is this? This one is having a constant gradient. And it is true for uniformly increasing velocity. Is that okay? This is uniformly increasing, that the velocity is increasing uniformly. To mean increasing uniformly means that maybe say after every 5 seconds, it is adding the same value of velocity. So there I will say the velocity is increasing uniformly. After every given time, the same value of velocity is added. It is added. So we say it is a uniformly increasing velocity, and it is a constant gradient. And even if you calculate the gradient here, you calculate the gradient here, you will be in position of getting the same value. Therefore, we say the the gradient is the same or constant. And if that is happening, it means that the body is increasing the speed, but it is increasing the speed uniformly. Like I've told you, it would also mean that if a body is moving, it is increasing the speed. In every 2 seconds, it may be putting 5. Another 2 seconds adds another 5. Another 2 seconds adds 5. There we say the body is having a uniform velocity increasing, isn't it? An increasing uniform velocity. That is for, this one is for uniformly accelerating body. This one for zero gradient is for stationary body. Is that okay? And now we can also look at this. Supposing I decided to have this here. If I decide to have that, this is displacement, and then I have your time. What is this? This is also constant. This is constant positive gradient. This is a constant gradient, but this is negative, and this is a positive gradient. If you calculate the gradient of this line here, you'll get it as a positive. Therefore, it is a positive gradient. If you calculate the gradient of this, you will get it as a negative. I'm calling it constant gradient. It is constant because even if you look at calculating the gradient here, or here, or here, you will get the same value. Therefore, we can say this is a constant gradient, but they will always be negative. The same value, but negative. Are we there? So, and what is true with this? This is uniformly decreasing velocity. That after every 2 seconds, the body is maybe reducing the speed by 3. Another 3 seconds, it reduces the body by 3. Another 3 seconds is reducing by, is that okay? So that's what we're calling uniformly decreasing. The velocity is decreasing steadily. Is that okay? The velocity is decreasing steadily. The graph looks like that, with a constant gradient but a negative value. And then, if we look at that, why can't we look at this? Why can't I look at this now? This is still displacement in meters. And then I can look at this one time in seconds. You're supposed to write down the full one, displacement. Displacement in meters, time in seconds. Supposing I look at this. Look at that, very interesting. What is that one now for? What do you think will that one be? This one is a varying gradient. Okay? This is a varying gradient, and the gradient here is different from the gradient here. This is varying gradient. varying positive gradient. This is a varying gradient. And this one is for increasing speed. Increasing velocity. I can call it that. Increasing velocity. The gradient is varying, and we're saying that is going to work for increasing velocity. The other one was uniformly increasing velocity, but this is just increasing velocity. What does that mean to us? Increasing velocity. That means that the velocity is increasing, but not uniformly. In that, in 2 seconds, the body can add like 3 meters per second. In another 2 seconds, it can add more than that or less than that. That means that the velocity is increasing, but not steadily. It is not adding the same value again and again. That like here we're saying that every 2 seconds it is adding 5. Another 2 seconds, 5. Another 2 seconds, 5. If that is happening, we say it is a uniform lay. It is a uniform 5. 5 is being added after every 2 seconds. Then it comes up with it. It comes out up to this point here. But should it be a scenario where we are looking at every 2 seconds, you add 3, another 2 seconds, you instead add 4, another 2 seconds, you instead add 5. That means that as the velocity is increasing, it is not increasing by the same magnitude. Therefore, we don't say uniformly. It is not uniform. We just say it is an increasing velocity. Whereas this one is saying uniformly increasing velocity. Is that okay? Let me hope you're getting the difference between this graph here and this graph here. Is that okay? And then let's look at this kind of problem here. Should I draw it here? This can be also still my displacement. And then I can have your time. Okay? And then I can have this here. I can have that there for you. This one here can be decreasing velocity. That when the velocity is decreasing, but it's not decreasing uniformly, that now will work as our velocity displacement time graph for a body decreasing its velocity. So this is so far under displacement time graph. We said displacement time graph for a body which is at rest, you draw with the horizontal line, 0 gradient. That means the body is at rest. And then if you draw and then do that, this is displacement time graph. This is displacement time graph, but for uniformly increasing velocity. And then if you have this constant graph for uniformly decelerating. If you have this, that is varying gradient but increasing the velocity, but not steadily. And now this one is for decreasing the velocity. Is that okay? And then after looking at this kind of graphs, let's look at the next graph, and that is none other than velocity time graph. Let's look at velocity time graph. So, velocity time graph. Can we look at a body moving with constant velocity? We say part B. Let's look at velocity time graph. Velocity time graph. So let's see what happens under velocity time graph. I have this. I can have my time. Now here is V in meters per second. Supposing I have that. Can someone tell us what is very true about that graph? That if I have a graph which is looking like this, and is a velocity time graph, what do you think is true about that graph? It is also very important for someone to note that the definition of some element we are going to see ahead, acceleration, which may be new or not to you, that acceleration is the change in velocity divided by change in time. We shall look at that as well. But that is the definition of acceleration, the rate of change of velocity, or change in velocity with respect to time. So, if I have acceleration as that, that means that change in velocity. If we are looking at smaller changes, we can just say that is the V, because we are looking at velocity, over change in time is the T. So that means mathematically, we can treat this statement of change in velocity over change in time as the dv dt. Is that okay? It is called dv dt. Now, coming back to our graph here. This graph is showing us that if, take an example, if here I have maybe 5 meters per second, that means that as time is going, the velocity here is 5, the velocity here is 5, the velocity here is 5, but time is changing, but the velocity is not changing. That means that the change here, dv, is 0, there is no change. 5 minus 5, 0, there is no change in velocity, but time is changing. If I have 0 change, 0 divided by that is equivalent to 0. That means acceleration is that okay? This is for 0 acceleration. What we call constant velocity. The body is moving, but it is not changing its velocity. That everywhere, if it has remained on 10 meters per second as the speed, as the velocity, it will remain there 10, everywhere 10. That implies that it is not accelerating. In other words, it is not increasing the speed. Are you getting that? So that's why we are saying that we should draw the graph to look like that. If the body is moving with a constant velocity, we can also say it has 0 acceleration, isn't it? Because we said acceleration is change in velocity over time. So if there is constant velocity, that means there is no change in velocity. If we divide by the time which is changing, provided the upper one is 0, not changing, that means acceleration is definitely 0. And we conclude that for a body moving with a constant velocity, acceleration is equal to 0. Is that clear? So, and the velocity time graph for such a scenario is what I've exactly drawn. It is what I've exactly drawn. Is that one there? 0 acceleration or constant velocity. Okay? Let's look to the next one. Let's go to the next one. If I decide now to draw something like this for you, I draw, this is velocity in meters per second, and this is time, that is time in second, and then I have this, I have that, I'm looking at it being at the origin, please, is at the origin, eh? What do you think is that? Moreover, velocity against time, velocity time graph. What do you think this one is portraying to us? A constant gradient. First of all, it is a constant what? It is a constant gradient. This is a constant gradient. What is that constant gradient all about? Can you imagine? What is this constant gradient all about? This is what we are calling the uniform acceleration That the rate at which the velocity is changing. The rate at which the velocity is changing. The rate at which the velocity is changing is uniform. Is that okay? The rate at which the velocity is changing is uniform. Is that okay? So that means that we are looking at the speed. I mean the acceleration is a uniform one. Because we are looking at that in every time interval, the velocity is increasing by the same magnitude. We call it please, let's not contradict it with the other one. When we talked about something like this, when there was displacement with time. Here, what is very true is that the distance is increasing by the same time, that in every given time, maybe in every 2 seconds, the body adds the same distance. In every 2 seconds, it adds the same. Maybe if it is adding 5 meters, it means that every 2 seconds, it covers 5 meters. Another 2 seconds, 5 meters. That is what this means. That the time is increasing at the same pace with the increment of the displacement. Every 5 meters, every 2 minutes. An example, you increase the distance or you cover 5 meters. Another 2 seconds, 5 meters. That is what we are meaning here. But here, every 2 seconds, you increase the speed maybe by 5 meters per second. Okay? Here we are looking at it, distance changing steadily with time. But here velocity changing steadily with the time. And if distance is changing steadily with time, we say uniform increasing velocity. But here we say it is uniform acceleration, because by the fact that we are saying it is acceleration, that is already an increment. We don't say uniform increasing acceleration, we say uniform acceleration, because the moment you mention the word acceleration, you're already looking at a positive change, which is an increment, isn't it? So just say it is uniform acceleration. That is when a given velocity, is increased over a constant time interval. That if you started at 0 at rest moving, in every 2 minutes or seconds you increase the speed by 5. Another 2 seconds you increase the speed again to 10. Another 2 seconds you increase it to 15. We call that one uniform acceleration. But if in every 2 seconds you cover a distance of 2 meters, 5 meters. Another 2 seconds you add another 5 meters. Another 2 seconds you add another 5 meters. That is what you're calling uniform velocity. Is that okay? Like you add in every 2 seconds, you put a distance of 5 meters. Another 2, that means now 4, you go to another 5 meters to go to 10 meters. And then another up to 6, you're adding 2, and then the distance also you're adding 5, 15. To 8, you are going to 20. Like that. If you're doing that, what we are talking about is this. We say you are increasing the velocity uniformly. But if it so happens that instead you are saying that after every 2 seconds, you increase the velocity by 5 meters per second. Another 2 seconds, you increase by 5 meters per second. Here it is meters, but here velocity is the one we're increasing. We say that is uniform acceleration. Clear? Let me hope we have gotten the difference between the two. So, we need to make more clarity on that, on uniform velocity and uniform acceleration. Uniform velocity is if we are changing, uniform velocity is when we are changing our distance by in the same time interval. We are changing the same amount of distance. Is that okay? And now for uniform acceleration is when we are changing the speed by the same amount in the same time interval. That is what we call uniform acceleration. Uniform acceleration. And then let's look at this graph here. Supposing I have that, and this is velocity, and then this is my time. This is also constant gradient. But it was negative. This is the uniform deceleration or uniform retardation. All the same. And write this simple one here. Retardation or deceleration. Deceleration. Is that okay? So, if we have our graph in this format here, we say the body is reducing the speed by same amount over a given time interval. Is that okay? That after every 2 seconds, if it was moving with 100 meters per second, we would say that every 5 seconds, it reduces it by 10. That means it comes to 90. Another 5 seconds, it reduces it to 80. Another 5 seconds, it reduces it to 70. Another 5 seconds, it reduces it to 60. We say it is uniformly reducing that speed. Is that okay? We say that is a uniform retardation or a uniform deceleration. Is that okay? That is the graph for a body which is reducing the speed uniformly. After a same time interval, you subtract the same amount of velocity. If you were at 100 meters per second, you reduce to 90. You reduce the speed to 80. The time is also the same. We say you are uniformly retarding. Whereas this one is, you can be increasing by the same amount. From 0 you go to 10 meters per second. From 10 you go to 20. From 20 you go to 30. If you are doing that in the same time, we say you are uniformly accelerating. Okay? Good. And then we can also look at this graph. Good. This is also still velocity in meters per second, and then time in second. What should that one now mean? We have looked for velocity, we have looked for displacement time graph. We say that is the body which is just increasing the speed, but not uniformly. So that means this one also would be acceleration. The body is just increasing the speed, but not by the same. That it can increase it from 0 to 10 in 2 seconds. I mean in maybe 5 seconds, from 0 to 10 meters per second in 5 seconds. And then increases it to 30. From 10 to 30 in still 5 seconds. Are you getting that? That you are using the same time interval, but the speed you are changing it by a higher rate. You change speed, you change by a given bar, and then increase it again. The changes are not uniform. Yeah? Initially you started at 0, maybe by 5 seconds you got a speed of 10. And now another 5 seconds to make it now in 10. Yeah? Another 5, you increase it again to 30. Isn't that change? The time increased by 5, but the velocity here increased by 30. It was supposed to be 20 if it was to be uniform acceleration. But by the fact that you took it to 30, that means you have increased it by 20. You didn't increase it uniformly by 10, because from 0 to 10, that means you have increased by 10. From 10 to 30, you have increased by 20. You are not increasing by the same amount. Therefore, we say you are just increasing the speed, or you are just accelerating, but not uniformly, like we said in velocity, in displacement. Is that okay? To be uniform, it means if it is velocity, if it is the displacement against time. To be uniform, we say that you are covering same distance in the same time interval. You will be adding every 2 meters, I will be covering 10. Every 2 seconds, I will be covering 10. We say for you are uniformly increasing the velocity. Is that okay? That is uniform increasing velocity. And then if at all now you keep on increasing the speed, but you keep on covering the distance somewhere in 2 seconds you cover 10, another 2 seconds instead you cover 20. There we say that you are not, your velocity is not uniform. You are just increasing it, but not uniform. The same idea applies to this. So this is velocity time graph for acceleration, and the same thing also works for this. This is velocity in the meters per second against time in second, and this is deceleration or retardation. That is deceleration or retardation, but not uniform. Is that okay? And then lastly, I can now look at this. What about that? That is a velocity time graph for a body which is uniformly accelerating but not from rest. The rest are from rest. Okay? This one is for a body which was also already moving. This is from rest, from rest, from rest. And now this one had some velocity but reducing it. This one is increasing the speed. But the speed, it was already moving at some value. Before timing, it was having some velocity. So when you say now it began, there was some velocity which was there. So this is the velocity time graph for a body increasing the speed but not from rest. Initially it was moving with some speed. Whereas this one, they're increasing the speed, they started right away from rest. Is that okay? So this is our velocity time graph. Is that okay? So we should be in position of understanding all these graphs. Velocity time graph, acceleration time graph. We said if it is like that, that is the body moving with constant velocity. In other words, zero or no acceleration. If the body is moving like this, we say the body is uniformly accelerating. Okay? It is increasing the speed uniformly. In other words, for the same time interval, there is the same speed being added. For the same time, the same speed is it that if you say after every 5 seconds, I'm going to be increasing the speed by 10. Another 5, I increase also by 10. Another 5, I increase by 10. We say you are uniformly accelerating. And then if you also say every 5 seconds, I will be decreasing the speed by 10, I drop it down. We say you are uniformly retarding. Is that okay? And then also we are also saying that if you increase it anyhow, not saying every 5 I will do to this. Yeah? You can maybe say in 5 I will first reduce I will increase by 5. In another 5 instead I will increase by 10. In another 5 I will increase by different amount, which is not constant. We say you are accelerating, but not uniformly. And then if you are doing that for reducing the speed, we say you are decelerating, but not uniformly. The same thing we talked about displacement time graph. That if it is displacement, if it is uniformly increasing the speed, we say you are, for the same time interval, you are covering the same distance. Okay? For the same time interval, you are covering the same. In every 5 seconds, you are covering 10 meters. Another 5 seconds, you are covering 10. We say you are uniformly increasing the speed. If it is this, if this is displacement and this is time. Okay? This is the uniformly increasing velocity. Uniformly increasing the velocity that in every given time you cover the same distance. The same time, same distance added. Another same time, maybe the time is the same by 2. 2 you're also adding, I'm covering 10, 10, 10. We say that is uniform uniform increasing. If it is like this, it means that in the same time interval you are also you are decreasing the speed. You are decreasing the speed going down. So that is so far under our ideas of graphs. Is that okay? That is under our idea of graph. So after looking at all those graphical ideas, can we see how this graph can be used in solving problems? Can we look at how we can use all the graphs we have to solve problems of calculating the distance covered, calculating the acceleration of the body, calculating the time taken, something of the kind? How do we use these graphs? How are these graphs relevant to our idea? Is what is supposed to come next. So, we are still under graph. Calculating the acceleration and the total distance and the distance using a graph. How do we calculate acceleration? Calculating acceleration and distance using a graph or even a velocity. Let me make it general. Calculating distance, velocity and acceleration from a graph. That is what we should be analyzing now. So, I can say consider a graph of y equaling to mx plus c. Is that okay? Let's consider a graph of y equaling that. How does that graph look like? If you plot y against x, that graph will look something like that. And now in this case here, c will be your intercept. Okay? And the slope here will be m. Does then that graph look like that? Velocity, the y-axis graph. The gradient will be the slope. The intercept will be the y-intercept. And then x will be that. And then I can say, comparing with the first equation of motion, which is v equaling to u plus at after rearranging, we shall say this is equivalent to v equaling to 80 plus u. So if we compare this, mx plus c. If we now compare with the first equation of motion that we are going to derive ahead, this is the first equation of motion. If we compare it with our equation here, after rearranging it, because u plus at can be written as a plus u. So if we compare it with this here, you will realize that this is that, this is that, this is that, and that is that. So it will mean that I can draw this graph. Where there is y here, I can put v. And where there is c, I can put u. The graph still will be like that. And then what we are calling the slope, here, as we are plotting x, for us we are plotting here t. X is t. What we are calling the slope is the gradient. What we are calling the slope m, for us is acceleration. So that means that the slope here is acceleration. So if we have velocity time graph drawn in this format here, the moment you calculate the slope of velocity time graph, it gives you acceleration. The slope of velocity time graph gives us acceleration. That is from our comparison. Because in this one the slope was m, but for us the slope is a, and in this equation a is acceleration. That is enough to tell us that the slope of velocity time graph is giving us acceleration. So if I extend this one here, and maybe I say the time to cover this, if it is t, and then this is u, and then v, okay, and then if v is there, and then I can call this one, if this is point O, A, B, C. Is that it? What is the gradient? We can now go through proofs. What is the gradient of the line AU? It will be change in V over change in what? Change in T. Change in what we plotted vertically against change in what we plotted horizontally. Is that okay? The gradient of this line. What is the gradient of this line here? What is the gradient of that line? Is what you're talking about. So it will be, you can draw that, Change in what is here over change in it. It's like here if you say what is the gradient? It is change in y over change in x. Where y is what is vertical. So it can be change in v, okay, over change what is here. Because for us, instead of x we have t. Instead of y we have v. So you can now say the grad here will be AB over what? The horizontal over OC. It could be this or this, all the same. And what is AB in terms of velocity? Because it is changing the velocity. It is V minus U. What is the change here? The velocity here was 0. Now up to here, the change is t minus 0. OC is t minus 0. So that means that gradient of AU is equaling to V minus U out of t. But if you look at this, change in velocity over time is acceleration. That means that acceleration is the slope of velocity time graph. That if you draw any velocity time graph and you decide to calculate the gradient of every part of the graph, you will be looking at the acceleration. Like if I give you example, if I have a graph which is like this, If you calculate the gradient of this, if this is velocity, this is time. If you look at the change here minus the change here to calculate the slope, what you'll get is acceleration. The same thing if you look at the change here over the change here. Okay? How is y changing? How is this one changing? Change in v over change in v over change in x in t will give you also acceleration here. The same thing here. You know how to calculate slope. Or if you are not getting it, we shall look at more clarity in our next example. So, but before that, put in your mind that acceleration is the slope of velocity time graph. That if you want to know acceleration, calculate the slope of velocity time graph. Are we there? Remember we said that we are going to look at how do we use graph to calculate distance, velocity and acceleration. And we said that we can consider this graph here. The graph of y on mx always looks like this, where y is on the vertical, x is horizontal. And this line is a straight line, but because we have intercept c, it is the y-intercept it cuts, and the slope will be m. So we said if we have the first equation of motion, which is v equaling to u plus at, if we rearrange it to be v equaling to at plus u, and we compare it with this, you realize that y is the same as v, a is the same as m, t is the same as x, u is the same as c. That means where there is y, I can draw the same graph. Where there is y, I put v, because y is v. Where there is c, me I put u, because they are the same here. Where they are putting c, me I will put u. And then where they are putting t, where they are putting x, they are putting x here, me I will put t, because x is the same as t. And it is very true that if the slope here is m, here the slope is a, and a is acceleration. That is also enough to tell us that the slope of velocity time graph, because this is velocity against time. Is that okay? This is the graph of velocity against time. Velocity time graph, the slope is acceleration. If we want to prove it by calculation or by derivation, we can now come and say, what is the gradient of UA? Is that it? What is the gradient of, actually at this point I would have called it some other letter. I would have called it some other letter N, so that I can say the gradient of NA is changing that over that, such that I can now say, because U is from here up here, it's not just the point. So what is the gradient of NA? What is the gradient of NA? The gradient of line NA. Gradient of grad of line A. But even if you leave it like that, it will be understood. Grad of NA, this line here, it will be, if I have this line here, I want to know its gradient, it will be changing what is plotted here over change what is plotted here. Is that okay? Like if I have this one as xy, it will be changing y over changing in x. But for us here vertically, we have v, horizontally time, so it is changing in velocity against changing in time. But from here, if we are looking at this, what is the change here? It is the AB. And then what is the change here? It could be NB. Isn't it? It is the OC stroke NB. You can say it is the OC because even OC is the same as the NB we are talking about. So here can be NB or OC. And then we said that, but what is the AB? AB is this, which is the same as the V minus U. V minus U divided by the change in NC. Do you say from here up here is the T? That means that it is the T, T minus 0. T minus 0, you can just say T. So that means you have V minus U out of T. But if you see V minus U out of T, this expression is for acceleration, isn't it? So that means that gradient can be equal to, because this is, you are calling this a gradient, but at the same time we are saying it is an expression for acceleration. So that means it's enough to say that acceleration is a gradient. So we draw conclusion that acceleration will always be the gradient of velocity time graph. The moment they say they sketch the velocity time graph and they ask you for acceleration, please don't forget to calculate the slope. That is that. And then what about if we now talk about area under the graph? If the graph is now this, and that. If that is my graph. Area under the graph, it is a trapezium. Is there the shaded area trapezium? This is a trapezium. The area is a half h into a plus a. Is that okay? That is if you have your trapezium is like this. H is this, A is this, B is that. So that is a half, okay? A half h. H is OC. What is AB? A will be here, B will be here. That is U plus V. A is U. Yeah? And then this one here will be V. But what is OC? Actually, let me first say A will be equaling to ON plus A CA. A is this, which is ON. And then B is the base, that is CA. And now you can say it is half times OC is T plus ON is U plus CA is V. OC is T. ON is U. CA is V. Isn't it? From here up here is V. And if you look at this properly, a half into U plus V times T. This in our derivation, this is the same as S. Is that okay? This is standing for displacement. That distance will be equal to average velocity times time. Is that okay? Displacement is the same as the average velocity times the time. And if you see here, this is the average. If the body moves from U, having velocity U, increased it to V, the average is U plus V divided by 2. So that means that this one alone is average velocity times time. That is already displacement. And remember, we are looking at area under the graph, but the formula which came out from that expression is the one of displacement given by average velocity times time. So because we say average velocity for a body having initial velocity U and increased it to V, the average is the same as getting the mean. U plus V divided by 2. That is average. When you multiply it by time, we are getting displacement. And that brings us to the conclusion that the total area under the velocity time graph is always displacement. Is that okay? So, from everything we have tried analyzing, you should master two main components. That if you plot the velocity time graph, if you sketch a velocity time graph, you should always master that if you sketch the velocity time graph, what is always very true is that the slope of that velocity time graph, the slope of that velocity time graph is always giving you acceleration. Is that okay? The slope of velocity time graph is always acceleration. Clear? The slope of velocity time graph is always acceleration. And then next is the total area under the graph. The total area under the graph gives you the displacement of the body. I'm repeating this, and I say, note, or I can say conclusion. What is very important, conclusion, is that the slope of velocity time graph gives acceleration. That is 1. 2, the total area under the velocity time graph gives what? Gives the distance covered. Before we do any example, make sure that these two, you know them. That if they ask you to sketch the velocity time graph, you should be in position of knowing these two, because they will help us. That the slope of velocity time graph will give you acceleration, and the total area under the graph will be the distance covered. Let's look at an example. Those are the main things you do understand under what we have been deriving. Let's have some example here.